Right here. Yeah. So it's 10 o'clock and we can officially start. Let's go to the start of the presentation. My name is Sajjad, and I'm a visiting faculty here, and this semester we want to talk about deep generative models. The first important point is that this class is being recorded, as you may understand. So make sure that your considerations are satisfied with this recording. And the most important point is that with that camera, the front side of the class is being recorded, and also the voice. And if you ask some questions, your voice will be recorded too, because the microphones are there and there is not a dedicated microphone for me. Great. I have sent this presentation for you. Do you see that? So we are ready for a quiz. Just kidding. As I say, I'm a visiting assistant professor here, and for 1 year, one semester has finished, and the other semester is starting. I'm originally from Sharif University of Technology, and I am on a sabbatical leave currently. In the CICS building, I'm in the Security and Privacy Lab, room number 226. And my own research areas are adversarial training, generative models for the objective of adversarial training or adversarial robustness, and also optimization methods. The TA is here and also here. She will help me during this course, and I hope you also enjoy it. About the contact with Shi, you can send him private posts on Piazza, and also he has 2 office hours, 2 separate hours during the week. He will set them with you. Shi, you want to set it now, or?
We can talk about it later.
Okay, good. And also this image that I sent you in the canvas. As you see, the canvas for the course is also activated. So, we start with logistics today, 1 session. Then we have 2 sessions for the introduction. This is the day that we start this topic, and this is the number of sessions. Then we talk about the autoregressive models for 3 sessions. Then we talk about variational autoencoders for 4 sessions. These are the topics for the first homework, and the due time for the first homework is the March 4th. And then we continue with normalizing flow models for 4 sessions, then generative adversarial nets for 4 sessions, energy-based model for 3 sessions, and diffusion probabilistic models for 4 sessions. And finally, in 1 session, we will talk about the evaluation methods. These are the due time for the homeworks, and also the midterm. I'll also send you the location for the midterm too in the canvas. So, any question about the topic?
How long will we have?
For the homeworks, I will talk about homeworks in the super. Yeah, we should talk about the type and the load of homeworks. So the objective of this course is to fundamentally understand the generative models. It means that we work with theory in the classroom, and then you will see the applications in your homeworks. The homeworks will be separated into 3 different parts. We talk about the homeworks. As you know, different type of generative models are suitable for different type of input patterns. So we talk about different generative models irrespective of the input type. We talk about deep autoregressive models. We do not consider whether the input is an image or is for example, text or a speech signal. We talked about the model itself. Then you can easily apply it for different type of segments. We also talk about the training and optimization. This part is partially in the presentation. For example, for the GANs, we talk about some training and optimization tricks. But generally, you practice this item in your homeworks. And finally, real-world applications. In the homeworks, you have two types of applications. One of them are toy examples that the data sets are synthesized, and the other one is, to some extent, real-world. I think, for example, CFAR or MNIST, some type like that, which cannot be said real-world to a whole extent, but they are near to the real-world applications. What are the prerequisites for this course? It's very important to know. First, we have 2 sessions for the prerequisites, but in those sessions, I generally talk about the probability and statistics. Because I want to, we have a contract over the notation, and that notation will be built in those 2 sections. But we do not have other prerequisites. Maybe you need to practice them outside the class, and I'm ready to help you with those. So the prerequisites are probability and statistics, linear algebra, machine learning and deep learning, and Python programming. As maybe she's talked with you, we have, let's say, some programming exercises that have a high load to some extent, and they should be written with PyTorch. So be ready to use PyTorch, and if you are not using PyTorch, I recommend you to talk with she about how you can handle it. Okay. The other important point is that the presentation are tailored toward the theory. We talked about the theory part in the presentations. And the homeworks are divided into 3 parts. The first part is the theory part, which is similar to the topics we talked about in the classroom. We have a programming part with toy dataset. Maybe this part is present in one homework, maybe it is not present. Based on the homework, you may have this part with toy dataset, and finally you have programming part which you work with some real-world datasets. And the programming part is also skewed toward image applications. And I think we do not have, for example, text yet. Do we have any text?
Not yet.
Not yet. And they are tailored toward images. So another important point is that this course is not an introduction to deep learning. We assume that you are familiar with, for example, recurrent neural network. If you are to some extent familiar, we can easily work with each other to understand totally the topics. But if you are totally away from the deep learning era, I suggest you to...
Is it 642 or 690?
This is 690, yeah. Also, it is not an introduction to probability and statistics. We just have 2 sessions, fast review them. And also, it is not a general purpose graphical generative models. We just focus on deep generative models. And we do not talk about the general purpose graphical models in this course. So the grade distribution over different tasks is this table. You have seen it. It is not important. The important part is the date for the midterm. The date for the final is also, after it was finalized, I will advertise it in the Canvas. It is not finalized yet. And this is the grading scale. It is not very important. The grades are rounded and it may be curved. And about the extra credits, different approaches we introduce in this course can be implemented on toy examples that visualize the method. You can find, for example, interesting visualization of GANs in the internet. There are several examples for GANs especially. If you work to develop some types of those visualization for different methods we talk about in this course, it has extra credit up to 10%, and I really encourage you to work on that topic. At the end of the term, if we see that there are several different groups that work on this topic, we can set a meeting to present those visualization methods and then assign the credit to each of them. The course attendance and participation is not essential, but I encourage you to attend the class because the midterm and final are really correlated to the class, the topics we talk about in the classroom, and you can solve your problems here. Okay, about the late submission, you have up to total 10 late delays for all homeworks, and you can use 3 days for each single homework. After that, your grade is reduced by this factor, and also the solutions are released 6 days after the deadline. So at 6 days after the deadline, you cannot submit your homework anymore. Yeah.
Are unused late days refunded as extra credit on that day?
No, they are separate. Yeah, the extra credit is just dedicated to that visualization. Yeah, methods. Makeup exam is not scheduled, but for the people with legitimate conflicts or unanticipated emergencies that can be documented, we can have makeup exams. So, any other question about this part? Yeah.
What is the credit for the audit?
For presenting for the class?
Yeah, for the...
There's no extra credit for that, but I think it can help you to gain the other extra credit with visualization methods. Yeah, but the class itself does not have any extra credit. Yeah.
So will the homework run like 1 week or 2 weeks, or like how long should we expect them to run it? Secondly,
to run what?
How long should we expect to have to complete the homework?
As you see in this figure, the homework will be released. For example, this is the at the end of this topic, you have your first homework. Okay, 1 week before finishing this topic, the homework is released, and you have 2 weeks after we finish the topic you have time to finish your homework. Totally, you have 3 weeks. 1 week you do not finish the material totally, but in 2 weeks you have finished all the material, so you have 3 weeks to complete your homework. And it is enough. I talked with Shia.
Will we be able to have the first homework released before ad drops so we can like gauge the workload?
I think so. Yeah,
Yeah, I think so.
Yeah, I think so. Yeah. Any other question? Okay. So let's go to the academic honesty statement. We all know about, just to review for myself, I have this slides. Please avoid academic dishonesty, including cheating, fabrication, plagiarism, and facilitating dishonesty. And there are strict sanctions for dishonesty based on the university rules. And make sure, if you have you are wondering whether it is an example or a dishonesty activity, make sure to contact me or she for the understanding the exact case. And finally, if you click in this link, you can have further information about the cheating. I want to emphasize that please do not try us. We are she and also our graders are really strict toward the cheating, and it has really consequences. So missing a question, a homework, and dropping even the course is not worse than cheating and accepting the risk. I want to make sure that you do not see the solutions because we do not estimate the latent variables. We just see your paper, and if they are similar, we conclude that you have cheating. We do not understand that you just see once your friend's paper, and maybe your mind is biased toward the solution, and then this is the result. We just see the papers and we conclude that it is cheating. So I want to be strict about the cheating problem, and these are some other tips. So about the honesty, we are on the same page. About the course material, we have several materials for these topics. In these days, we have 3 great books. The book by Kevin Murphy, Probabilistic Machine Learning, the advanced topic. The second book, which is published in 2023. The book by Christopher M. Bishop, which is Deep Learning Foundations and Concepts. I see the book, and it is also a really great book. And as you know, Bishop has a very well writing style. And also the third one, which is dedicated to generative models. And also there are 2 great online courses, one by Stefan Wermon at Stanford Deep Generative Models, CS 236, and one for Peter Abil. We can find them online, and the videos, especially for this part, and especially for the current semester, is being released. Yeah, for the 2024, Peter Abil have released his presentations. Okay, about the LMS, Learning Management Systems, we will use Canvas for the material, as you see in the start of the semester. We use the Piazza for the discussions, and also Gradescope for homeworks and exams. How to contact me? My office hours for this course is Wednesday 14 to 15. The location, I think it is finalized. I will give you the information after this class in the Canvas. And if the time is not working for you, please send me a message in Piazza so we can set another meeting in some weeks. Okay, it's finished. So any other question? Now we want to talk with you, and then we go to the introduction. What do you think of generative models? What is your idea? What do you believe you should learn in this course? In this presentation, I will talk about it, but before that, I want to have your ideas.
Can you repeat the question?
What do you expect from this course?
To understand how they work underneath different components, different design decisions that help solve different problems in order to build a model that satisfies a certain task. Yeah.
Yeah, exactly. We do not focus on the architecture in this course. For example, I say that this is transformer. Transformer has key values, queries. I believe that you are familiar with that. It is not important at all, because you can replace for the idea to work, you can replace the transformer with the recurrent neural network. Maybe you are familiar with recurrent neural network. So I am not talking about, because if we talk about, for example, the transformer, we will miss energy-based models, which is a really important topic in the generative models. So we just focus on the ideas that try to generate data in a deep architecture. But it is not important what is that architecture. It is one of the architecture. All the architecture cannot be used, for example, for every type of generative modeling. But we know that we will talk about which architecture it is suitable, for example, for energy-based model, which is suitable for autoregressive models. We will talk about them, but we do not discuss about the detail of the architecture. Okay, if you do not have a question, we can start this presentation. Everything is clear?
Clear about what?
What?
Clear about what?
About the load of the course, especially about the PyTorch, because she emphasized that talk about the PyTorch. PyTorch is the tool you should and maybe you must use for the homeworks. If you are not familiar, it may be challenging for you. So let's start about the content. This content can make you familiar with the rest of the semester. Okay, we are all familiar with supervised and unsupervised learning. In this presentation, I want to change your mindset from a deterministic mapping into a probabilistic mapping. Just we want to have this objective. You know, why? Because in generative model, we cannot escape from probabilistic approach. They are based and they are built on probabilistic approach. You do not have any other choice to talk about them. So, what is a supervised learning? The supervised learning that you have seen before, a classifier. In a supervised learning, you have an observation. The observations are a vector. We will talk about the notation in the foundation in the next presentation. But the bold symbols are used for vectors. This is a vector, and this is an one-dimensional vector in a scalar. So we have n observations of a classification problem. For example, we want to discriminate between dogs and cats. You have n observations of dogs and cats. What are the applications? The application is classification as a very well-known application, is regression, and other types of applications. And what is the model? This is the place that maybe your mindset should change. In classification, we are looking for a conditional distribution function. Are you familiar with type of concept and type of all of you? Oh, great. So, in the training phase, what do? We define a loss between the output of this model and the label you have provided in your observation, and then you try to minimize the parameters of this distribution. The optimum parameters, which we call theta star, is the result of the training phase, and then in a new in the new phase, which is the application or test phase, you use the train parameters to provide the distribution for a new input. It means that, for example, you have a problem of discriminating between cats and dogs. So you should provide, you have two cases, cats and dogs. You want to define a distribution over these two types of categories. What is the suitable distribution or mass function? A Bernoulli distribution. A Bernoulli distribution can have two different types of outputs, 0 or 1. You can code the cats at 0, you can code the dogs at 1, and you should provide a Bernoulli distribution with a parameter theta. Make sure that you do not mix this theta with this theta. Let's say it have a parameter lambda. Lambda is the probability of dogs, and 1 minus lambda is the probability of cats. So the objective is just to tell me this lambda. This is because at the end of, for example, problems with two types of class, you have these functions which transfer u from the real numbers into a value between 0 and 1. Because it is the parameter of a Bernoulli distribution, and it should be between 0 and 1. Okay, this is supervised learning. What is an example of supervised learning? You are all familiar with the data set of iris data set. It has 3 types of different flowers: setosa, versicolor, and virginica, and they differ from the perspective of sepal and petal length and width. What happened? You in the training phase, you enter one of those observations into your model. This is a model, and the output of the model assign a probability for different outputs for y equal to 1, 2, and 3, and you have a reference output. Okay? In the training, you decide to update theta such that the value for the corresponding to this reference is increased, and automatically, because generally you use softmax here, the value for the other 2 ones is decreased. And then you go to the next sample. And in the test time or evaluation time, what do? You input a new a new image to your model, and the model is now trained. It can assign the probability for each type of the output, and based on a risk management here, which we call decision, you output one of the y, 1, 2, or 3. So what is inside this probability distribution? The inside can be, for example, a multinomial logistic regression. The multinomial logistic regression is a one fully connected layer and then a softmax mixing. The softmax, why do we use softmax here? What?
To convert nodes to probabilities.
Exactly. Because in this part, anything you have in this part, the output is a legitimate parameter for a categorical distribution. A categorical distribution parameter should sum to 1, and at the same time, each of these elements should be greater than 0. So the softmax just convert from an arbitrary vector here to a vector which is suitable as a parameter for a categorical distribution. Okay. And how about the unsupervised learning? In unsupervised learning, we have a data set, but the data set is just, the observation is just a vector. And you are trying to do several applications. For example, dimensionality reduction. These vectors are in a high dimension, and you want to preserve the information and at the same time reduce the dimension. You preserve the information maximally. For example, the application is clustering and other applications. For example, in the dimensionality reduction task, you have this type of model. You want to reduce the dimension of X using a match matrix W. And then training, you minimize a loss between this projection of input and the reference input, and finally, when you train it, you use it to reduce the dimension over new random variables. And this is the block diagram of the PCA, and this is an example of dimensionality reduction. You have these types of data. Based on the loss function we designed, we understand that the best direction to minimize the loss is this direction. Then you project the data onto this, let's say, subspace, and then you have one-dimensional data instead of two-dimensional. Okay, altogether in the supervised learning, we have two types at the input and the output. The applications are classification, regression, and semantic segmentation, and other applications. And your objective is to estimate the true probability distribution over data. And also in the unsupervised learning, you have these features. You have a data set like this, which we do not have an output for each input. We just have the vectors, and your objective is one of these, and your application, and the objective is to estimate the data distribution. Maybe you are not familiar with this objective, But you can check that. Having access to the data distribution, you can do almost all of the applications. So, any questions about supervised and unsupervised definition from the probabilistic viewpoint? Okay. So in the next section, we want to talk about the unconditional generative models. Excuse me, Sheet, do you have any?
Yeah, I have some meetings.
If you want to talk with students, you can talk and then I will continue.
I don't have anything.
You don't have anything? Okay, great, thank you. Okay. So, in this session, I want to talk about the unconditional generative models as an unsupervised learning models. So, what is the unconditional generative model? In the unconditional generative model, similar to unsupervised learning, you have this data set. It means that you do not have any label for your data set. You just have, for example, images of natural images, for example. You have a bunch of natural images, and what is your model? Your model is to estimate the, this is the problem. Your model is to estimate your objective is to estimate the true data distribution. I call it P data of X. What is your model? You have a parameterized model. How is this parameterization? It is the thing that we talk about in this course. What is the task? The tasks are a bit different from unsupervised learning. The first task is the density estimation. It means that if I give you a new sample, for example, you have images of dogs with a specified dimension, for example, 32 by 32. You have images of this type, and you train a model. We do not know how to train it. We want to understand in this course, but for now, assume that I can train it and I have access to this distribution. The first task is if I give you a new 32 by 32 example, can you tell me how probable is this is an image of a dog? I don't know, I forget. I talk about dogs or cat. If I talk about the dog, if I give you a new image, can you give me an estimate how probable is the image contain a dog? This is the density estimation. You give me a number, a probability. This is the first task. How can this be used in real-world application? Density estimation. Can you give an example in real-world that we can use density estimation? Maybe you are familiar with outlier detection or anomaly detection. You heard of anomaly detection task?
Yes.
Anomaly detection is really this task. Because why? For example, you are in the factory and you give images of, for example, their product. If the product have any defect, you should understand. So they give you several images of correct and suitable products, and you train the model. And then in their factory line, you start to capture the product. Each of them that this probability is very low, you understand that it is an anomaly. It is a defected material. It is a defected product. And you can, for example, reject that or go to the second line. So it has a real-world application density estimation. The other one is generation. If you train this distribution and you are capable of generating new samples, what does it mean? Give me samples of high probability. What do you expect of those samples?
Too much real data?
Yeah, exactly. To see dogs in those samples. Why? Because you train the model and you are giving me examples of the high dimensional points. It means that they are coming from the real distribution with high probability. So you expect that you see dogs in those samples. How can we use this images?
Generate synthetic data.
Exactly. For example, for CFAR, you have a accuracy state-of-the-art model. But nowadays, you can generate samples of CFAR and improve your model accuracy with those samples. So they are really working because they are exploring new point of the space that is not explored in the dataset, CFAR dataset, because the accuracy is increased. Okay? And the most important part, which is not clear yet, is to provide a high-level representation of the data. What does it mean? For example, consider the iris dataset. The iris dataset, if you look at the dataset in a dimension of, for example, in a high dimension, which we do not know, for example, Z1 versus Z2, you can see there is a suitable point, there is a suitable subspace, two-dimensional subspace. You do not have any label for iris, okay? But in that subspace, the samples of versicolor are here. I write here V. The status are here, and the other type that I do not remember are here. It is a great objective to retrieve Z1 and Z2, yeah? If you understand Z1 and Z2, you can, what is the application of this idea? For example, consider that I understand Z1 and Z2 for a sample. It brings me a high level of compression. You know why? Because you can convert an image into two dimension. An image 32 by 32 into 2. It is a very high, because in many cases, just the type of the flower is important for you, not the, for example, where is this flower image captured. Just, this is status, this is versicolor, what is this? Okay? So, this two dimension is much more important than 32 by 32. You capture just needed information. So this high-level representation is very high importance, and you will see that it can help you in different tasks. For example, if you train your dataset over MNIST dataset, and then you plot the data in this Z distribution, you can see that although you do not have any information of the label for MNIST dataset, they are clustered. Each digit is clustered in a point, and you can easily cluster them without access to the label. So, unconditional generative model are exactly unsupervised learning, but the tasks are these three tasks. And you know that each of them have real-world applications. And the objective is you have a data distribution. It means that the real-world data set is coming from a distribution. We do not have access to that distribution, but we have a model. We want to fine-tune the parameters of that model such that we have the lowest distance. The distances should be defined. We do not know anything about the distance. This is the topic of this course. We should define a tractable distance. The most important point about the distance is tractability. We should define a tractable distance, and then we should minimize that distance. How? By changing the parameters of your model. And hopefully, after the training, you can approximate the real-world distribution with your model distribution and do these tasks with your model distribution. This is our objective in unconditional generative models. So, what is generation? As you can see, if I train an unconditional generative model over iris dataset, I can generate samples of iris dataset easily. You know, capturing iris dataset is a very hard problem, but generating is really easy. We can do it by a computer. I can estimate the density. For example, assume that this density, this block is your model. Then if I give you an iris data set, you give me a large value, and if I give you, for example, a random noise, you give me a small value, and if I give you a image of, for example, Lena, you give me a small value. Why? Because Lena is not coming from the manifold of these iris states. So you should give me a small value. And also the latent representation, as I say, for the case of iris, assume that given the model, this is maybe seems a bit tricky now, but we will talk about this inference task that I can infer the latent representation or the high-level representation, as I said here, given the data point. And it is really applicative, really. Okay. So, any question about unconditional generative models?
I would have thought the next one had a bigger value. Oh, you still have a 2 to e to the minus 6?
2, yeah.
It's bigger than the others, but
yeah.
It's still pretty low.
Because the summation of this distribution over all images should be 1. So each of them do not, still have, but in comparison to this, it is very large. Yeah, exactly. But it is really a typical number. You have this order of numbers, when you train the model. Yeah. Any question? Great. So we want to talk about the conditional generative model. The conditional generative models are extension of supervised learning. But how? So, in the conditional generative model, you again have access to X and Y. It means that you have input and output, and you want to connect them. What is the model here? The model is exactly similar to supervised learning. You want to estimate the probability over Y given the input X. What are the tasks? The tasks are repeated. It is not important. Just you have a given X. It is not important for us. And the objective is again minimizing the distance between P of Y given X over in the data distribution and in the model distribution. So what is the task here? For example, assume that I have an image like this one, and I want to generate the higher resolution of this image. This is a task of a conditional generative model. Why? Because you have an input X, and you want to generate the samples corresponding to this X. Higher resolution of this image. This task is not, it cannot be done using unconditional generative model because they do not accept any input. But here you can easily give them this input and then generate the higher resolution. How? For example, this task is the density estimation. I give the model the low resolution image and ask him which of these is more probable to be the higher resolution of this image. So we expect the model to give high probability to this one and low probability to these ones. Yeah?
How are Y1, Y2, Y3 generated again?
They are, for example, I take them randomly. How generate YX, for example, is important. If I assume that YX is generated using a generative task.
I see.
Yeah.
I see.
Or in other words, for example, you have access to Y1 and then you downsample it. Yeah, and you have this X. Yeah. Okay. So we expect the trained model. Yeah.
Last question. Sorry. X new is some new data point, right? But you said Y1 is like you already have access to it, right? But I'm saying if X new, how do you calculate the score for something that is completely new? I'm guessing this. I understand the generative part, right? But you said you already have.
This is, you should pay attention. This is in application. We have trained a model. You know, what does it mean? It means that I have been given a set of low resolution and high resolution images, This is the low resolution. This is the corresponding high resolution. Let me.
Real quick, could you write further?
Oh, sure. You know why I write here? Because the guy from the CICS said that the camera cannot cover all the places. I think we can write until is here suitable. Assume that I have a set of low resolution and high resolution images. I train my model, okay? I train a model, and from this time, I can give this model the X, a new X. It is not the training yet. Training is finished.
Right.
This is a generative model.
Right. Yeah.
What can we do with this? You can give me new Y, and I can give you probability.
Yeah.
What does that probability mean? It means that given this X new, is the Y you given me, is the high resolution of that one or not? If it is, I should give you a high probability. If it is not, I should give you a low probability. On the other hand, I can be capable of generating Y. What does it mean? It means that the corresponding higher resolution images 2x.
Right.
This is the generation part. And also the latent variable is also another task.
That's good. Yeah.
It's okay?
Right, yeah. So Y is good. You get Y from a generative model, right?
Yeah. Any question? Okay. So, this is just the density estimation task. This is generation. For example, you have a train. As you see, I write here theta star. It means that we have a trained, finished. We do not know how, but we have a trained model. This trained model, if you give it a new X, what it generates is the high resolution of that X. It cannot generate, for example, faces of other people. It look at this X and generate higher resolution. It may generate for you several samples. You can generate different type of higher resolution and give it, for example, to a person and try to select the best one. But the application is that you can generate different samples. So the first question here is that why we cannot use our supervised learning models here? Because it is a supervised learning, yeah? What do you think of this question? Why we can easily apply, for example, logistic regression or deep learning. For example, deep learning terminated to a logistic regression is a complete classification and supervised learning. Why we cannot apply that model to this task?
You want as an output an image, not a classification. Right?
Yeah, exactly. The dimension of the output. Yeah.
We do have a prediction for every pixel in this case. Right? To generate an image, we predict every pixel so we can have a classification.
Exactly. I will talk about it. One idea is that we are predicting each pixel, and each pixel is through 0, 1, 2 until 255. For example, in grayscale images. So we can easily predict that image. We can have, for example, if you have 32 by 32 pixels image here, you have several, for example, classification problems, and you solve them all at once, and then you have a generative model. The most important problem with this approach is that the pixels are correlated to each other. It means that if you generate, for example, the first part, the second part is correlated to that part. And in your example, you neglect all those correlations. You are generating independent classifiers for each pixel. And you can see in the next slides that this cannot work in real world applications, even MNIST. Yeah.
I still don't understand the difference between the previous density and the generation.
The difference between these two? After the I just want to emphasize that there is no difference between the task of conditional generative and unconditional generative. If you have a conditional, it means that they must give you an input, similar to supervised learning. Then you have a distribution condition on that input. It means that if they give you another input, you totally have a different distribution for generation, for density estimation, for latent variable inference. Yeah. In other words, just to have a higher order of understanding. And in this part, you do not model the distribution over the X. This is the really high level. At the end of the semester, we can understand what does it mean and what does it practically use. Yeah. But for those who are familiar, for example, in supervised learning, how we do not have access to the distribution over the X, I say that here is similar to supervised learning, where we do not model the distribution over the X. X is an input. Yeah. And we believe that that input is really a legitimate input, not a, for example, outlier or noise, for example. If you give it the density estimation and noise, it also generates you a higher resolution of that noise, but both of them are meaningless. So, yeah.
Can you one more time explain what is Y1, Y2, Y3, and possibly in relation to the data on which the model was trained?
Yeah, exactly. Assume that I have a data set. This data set is Y1, Y2, and Y3 is not in the data set. I have a data set, for example, high and low resolution. How can I build that data set? I can easily take out high resolution images from the internet and then downsample them, mean that generate low resolution of them and generate the data set. So the data set is easily generated. So I have high resolution and low resolution. With the techniques that we learn in this course, you can model the distribution. So we do not know how, but we can, at the end of the semester, generate this distribution. Now you are in the application. You are given this distribution and a new sample. Assume that sample is this one. So, what does this model say? This model is trained to understand higher resolution version of what is its input. What is the input? It can understand what is the higher resolution corresponding to that input. So here I give 3 different inputs, and I know that one of them is the correct higher resolution corresponding to the X new. What I expect from this model, I expect that it can identify the higher resolution and also identify the irrelevant images. How? By making a large margin between the output probability value. And you can see it here.
Understood.
Okay? Any question?
So in the application stage, there are really 2 sets of inputs, like the set multiple.
Exactly. And this is the main important problem is that you do not model the distribution over X. X is input, exactly similar to supervised learning. I will talk about an example that, for example, X is for example, have missing values. In that set, you cannot do anything with this model because you do not model the X itself. You just model the output given input. You do not have access to it. We will talk about this in example. You can totally understand it.
So, isn't this very similar to classification? Because we are trying to see how close the input is to one of the Y's.
I know that this is really near to classification, but the dimension is the problem. You know, in classification, the Y is a member of this set, C. It is a one-dimensional random variable. So one-dimensional random variable like this random variable can be easily modeled using a categorical distribution with a parameter. But assume that you have even, for example, MNIST image, which is a really simple data set. The MNIST data set is 28 by 28. And you should model a random variable with this dimension, which is really huge. Even in comparison to this one, I mean. As he said, the problem is dimensionality. The dimensionality is the main important problem, and I have an example here why we cannot use our supervised learning models for a generative model. Assume I want to model a super resolution problem, super resolution, you see that before, where x is in this dimension. It is easily a binary image with r times c dimension. And the higher resolution is exactly another binary image with h times w dimension. Assume we want to use logistic regression as the simplest case with minimum number of parameters to do this task. So how many parameters do we have for this task? The MNIST dataset, I should provide a probability for each of possible outputs. Do you agree? This is the task of supervised learning. You provide a probability for each of legitimate outputs. How many legitimate outputs do we have here? 2 to the power of h times w. For a simple example, over MNIST, it is a large number. Do you agree? So, even with the most simple architecture of supervised learning, which is multinomial logistic regression, one of the simplest, we have k nearest neighbor. Even with one of the most simplest one, you have interactable number of parameters. So, what is the problem with interactable number of parameters? The most important parameter is the data set. You should have a factor, for example, 10 factor or 10 times this value training samples to train the model. And it means it is interactive. So you cannot use supervised learning techniques to provide conditional generative models. Do you agree with me? Okay. So, what a very important point is that although conditional and unconditional are really unconditional are similar to unsupervised, conditional are similar to supervised learning, but the framework to train both of them is similar. It means that you can do the techniques, for example, to do conditional generative modeling, and you can use it for unconditional. How? You just, for example, replace the input x new with null. Everything works. And in several generative modeling. And the most important part in generative modeling is the shared technique between conditional and unconditional generative modeling. So we do not talk about both of them in all the architecture, maybe about one of them in architecture, and you can easily extrapolate that for the other case. One notational important point. From this slides to the end of the semester, I will use p theta of x given y. Just change x and y. Why? Because we are, if I use this notation, I am always modeling a distribution over x. Because for unconditional, I am modeling p of x. For this case, I am modeling p of x given y. Just keep this point in mind that we use this notation instead of the supervised learning notation. It is really common in the generative modeling literature. Okay. So, any other question about generative, ungenerative? But yeah.
In the previous slide, where you were mentioning about the number of parameters, hypothetically, if we have a lot of resources, this will be possible.
Yeah, the most important part is that you know the high number of parameters, you are very near to the overfitting. Even if because you have lots of parameters, they are as I said to your friend that we are modeling we are ignoring the correlation between pixels. Those correlations really works in application. Because, for example, if you have half top of the image, you can easily infer something about the half bottom, you know? So ignoring them and high number of parameters makes you vulnerable to overfitting. Yeah. But if you have in mind that you have lots of images, it's an option. But it is not a real world because it's exponentially the number of increases with the dimension. So why do we need conditional generative modeling? Where they can be used? In contrast to unconditional generative, conditional generative modeling has lots of applications. For example, text-to-speech models. You give, we call them speech synthesizers. You give your input is an audio file. Your input is a text, and you want to generate the audio file for corresponding to that text. This is a conditional generative modeling task. Why? Because you have a high-dimensional random variable x, which is the audio file, given the high-dimensional text, because the text is also a high-dimensional random variable. So you have a conditional generative modeling, and you can see a sample of that here. Maybe I can play, maybe not, but you can play because the file is embedded in the presentation. You can embed it in your system. So this is one task of conditional generative modeling. Speech synthesizer, and some of the state-of-the-art speech synthesizers are really based on generative modeling like this. Other tasks, text-to-image. For example, you have a text. You are familiar with different platforms that provide this service for you. You have a text here, this text. And you want to generate a sample image corresponding to this text. This is again a generative modeling. Why? Because the random variable you are modeling is a high-dimensional random variable x. It's an image. You cannot do it with, for example, logistic regression or those other types that you have previously learned. And the other task is image colorization. How? You have your input is a grayscale image, and you want to colorize that image. The output is a high-dimensional image, which is, for example, 3. The depth is 3 in contrast to the input, which is 1. And you can see the colorized image and also the ground truth image, and you can see it really works. For example, the data set for this task can be easily generated. You download several colored images, you transfer them to the grayscale, and you have your data set. You can train the model, and then you can use it for colorizing different grayscale images, for example, the old images. Okay. Another one is image in painting. You have an image with missing pixels, and you want to fill those pixels such that the resulting image is a legitimate image. For example, this is one type of filling the missing values, and you can see that it really works, and the resulting image is a natural image, and you do not see any artifact in the image. You can see the papers also here. This is when I write the source, I mean that this image is exactly corrupted from the paper I provided here. Another task is image uncropping. You crop an image, we want to uncrop the image. You put one part of the image, for example, you missed a part of the image and I want to uncrop it. Again, you want to generate a you want to model a distribution over a high dimensional random variable X, which is an RGB image. You can see that, for example, for this image, which is the input to your model, the model generates this output. And another important point is that this is not the only output that the model can generate. You can sample another image from your model, several samples you can get from the model and select the best one. This is one of them, and this is the ground truth one. So again, you have a conditional generative model. Image restoration. For example, you have a noisy image, downsampled image like this, and then you want to create a higher resolution version of the image. This is again a conditional generative model, and you see the one sample here, and this is the ground truth, and you see that it really works. So, any question about conditional generative modeling? Yeah.
I'm a bit confused about the new notation you introduced, like x given y or y given x.
Yeah, because I want always to model random variable x. For this reason, I changed the notation from y given x to x given y. Why? Because in this example, again, I am modeling the random variable x. And in the unconditional generative model, I also want to to model this distribution. In both of them, I am working with x. You see in the notation, I use x1, x2. If I switch is in the conditional, I should x. In the unconditional, I should use x, and in the conditional, I should use y. And this, it makes some problems. I think, next week.
So does this generalize to having a vector of inputs as well? I'm thinking of the case when we want to be able to give it different images, and let's say it wants to mix two images. You want to generate an output that fits. I was wondering if all of your notation and every concept that you talked about generalizes to a vector as an input.
Yes, can be easily generalized. Before this course, you are all familiar with modeling this distribution where x can be high or low dimensional, but y should be low dimensional before this course. After this course, we hopefully can model this distribution where x can be high or low, y can be high or low. It means that the complete set. Yeah. But the most challenging part is when y is high dimensional irrespective of x. Sorry.
No, are there ways we can bias the sampling of x so that we almost get a specific type of output every time we sample?
In conditional or unconditional?
In unconditional. Okay. So, for example, there we're modeling f of x given y.
Yeah.
So when we sample x, we can get various types depending on how we train the model. So what I'm wondering is it possible to bias the sampling of x so that we consistently get a type of output that we want?
Oh. You mean you want to repeat your experiment and get the similar results?
Yes.
You can get the similar results by, for example, fixing your seed. Because in the generative modeling, you start to sample from some distributions. And based on the result of the sampling, for example, your image is generated. Okay? If you fixed your seed, you can generate exactly the similar image you have previously get. But the powerful aspect of generative modeling is that you can generate new samples. For example, condition on a low resolution, you can have different higher resolution version of that image. It is the power of the generative modeling. It is not a deterministic mapping. When you have X, you know Y. No. When you have X, you have a distribution over Y. And the point with a higher probability are better points because they are corresponding.
So yes, that makes a lot of sense. I guess what I'm trying to ask is when you say how certain types of domain, so if it's text, when you have creative writing versus academic writing, those are very different. And if you're sampling from a distribution like that, and you want to skew it to a specific domain, it sort of makes sense to me that you would want to bias the sampling in some way.
Maybe if I understand your question correctly, we can do it, for example, by because you have a condition, that condition guide you toward your objective.
Exactly.
Yeah. By tuning that condition, you can generate samples more related to your objective, to your domain. Yes. But we can talk after the class further. Any question? We are at the end of the class, but I want to just have some notes about the sequel of this presentation. I want to say that you previously see some generative in the sense of really high-dimensional models in the classification. The multinomial logistic regression, as you see, it is unsupervised. It is a supervised learning method it is a discriminative method because you model the output given the inputs. This is not important. This is the definition of the parameters. Just look at this formulation. Given the input X, you give the user a categorical distribution over Y, which is generated using affine transformation over the input and cross through the softmax function. The softmax function is just to make the parameters suitable for categorical distribution. This is the definition for the parameters. So if I give you an image, you can vectorize it and then give it to your logistic regression. I know that it cannot work in practice, but assume that it can work. So I give you this image, you transfer it into a vector, and then in the output, the logistic regression gives probability over these three different types of rooms: living room, bedroom, or dining. But you have, that you again have a generative model, but it is a very simple generative model. This is again a generative model. I can sample from this generative model, and when sampling from this generative model, because the second input, the second parameter have a higher value, it means that you generally see the second output in your realization, in your sampling process. Again, you have a generative model, but a generative model over a low-dimensional random variables. But for example, in discriminant analysis that we will see in the next session, you have also have a generative model over high-dimensional random variable, and you can generate samples from rooms. We will see this in the next session, and we will see how it can help you to handle challenging parts. When, for example, the X, which is given to you, it has some missing pixel, is noisy, for example, is a low-dimensional, which cannot be easily seen by human, and some deficiencies like that. Okay, if you have any questions, I'm here. If you have not any questions, you can leave it.
Can you go to the previous?
The previous?
Yeah. Can you explain the condition?
This one?
Yeah.
I mean that when you have a logistic regression, given input like this, the output of logistic regression is a categorical distribution over the labels. These are the parameters of that categorical distribution for these images, okay? So if I sample from this categorical distribution, what happens? Because the second label, the second parameter is higher, I generally see that in the output.